Is presentation visible?
Yes, sir.
Yes, sir.
Shall we
Yes,
start?
sir.
Yes, sir.
Yes, sir.
Okay.
Okay. So today we first discuss about canonical transformation. As we know, transformation means uh, one kind of change. Suppose we change, transform a variable to one to other. In some derivative and integration, we actually transform a variable y to t or x to t. Okay, that is known as transformation. In our mechanics, we consider particularly two kind of transformation. One is point transformation, another is canonical transformation. Uh, Point transformation basically means one point. Suppose it has a one coordinate, and we change one coordinate to other. It has let's say x, we convert it to y, or small q to capital Q. Maybe it has a number of coordinates q1, q2 to qn, then it will be capital Q1, capital Q to capital Qn, n number of coordinates. So that no, point transformation one to one transform q to q1, small q1 to capital Q1, small q2 to capital Q2, small q3 to capital Q3. Okay, and that done in your normal space, which is known as a configuration space. Mm. Okay. The transformation from one set of coordinates qj to a new set of coordinates capital Qj can be expressed by this equation. Capital Qj is a function of small qj into t. Just like your y, you put y is equal to 5t or y is equal to xt. So it is a function of qj and t. Uh, Such transformations are called point transformations. Okay.
Okay, sir.
Uh, like, 1 minute, please. Let me go. Hello. 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 हाँ और दूसरी लिखी नहीं कौन हम इससे की तरह लिखी हुई पेज पे तो हाँ लिखी दो मुझे इसे सेटा कि ये आप जो आने के ठीक करेंगे तुम लिखी दो ओह हाँ अरे okay. So this is called point transformation. That coordinate changes in configuration when one coordinate q1 to capital Q1, q2 to capital Q2, just like your normal substitution. It is a point transformation. As configuration space, uh, in normal space, here configuration space, uh, if it is a three-dimensional space, it has three coordinate x, y, z. If we have n number of particle, then we have three n number of coordinates. Then in configuration space, a system of n particle of three n coordinates x1, y1, z1, x2, y2, z2, x3n, y3n, z3n. Okay. In configuration space, the transformation is for point transformation, transformation of only position coordinates. But configuration space describes only position coordinates, so a transformation of position coordinates. So, another space we already discussed in the last class called phase space. What is phase space? Hello? Anyone please? What is phase space?
In phase space, every point has three coordinates for position and three coordinates for momentum. Total
Yes.
six can
Six
coordinates
for
are
one
there.
particle, six coordinate. So for
For
n
one.
particle, six n coordinate. And
Yes, sir.
in phase space, the path represents the actual path of motion because a position is fixed and momentum fixed means energy is fixed. And momentum is equal to 2 m root over. If you know exactly its momentum, its energy will be fixed. So the path in the phase space is the actual path of motion. So in phase space, the transformation is known as canonical transformation. A transformation both in position coordinates and momentum coordinates. Canonical transformations are the transformation of phase space, the simultaneous transformation of independent coordinate qi and pi. position and momentum to a new set of coordinates, capital Qi or Pi, capital Pi. With the equation of transformation, capital Qi goes to capital Qi, which is a function of small qi, small pi and t, and capital Pi is a function of small qa, small pi and t. Okay, so you can say it is a point transformation and phase space. In point transformation, we have only one coordinate, that is a position coordinate. In phase space, we have two kind of coordinate, one position coordinate and one momentum coordinate. So canonical transformation is basically a point transformation in phase space. Okay. So it's both position and momentum coordinate changes. The canonical transformation, why it named so? The canonical transformation are characterized by the property that they leave the form of Hamilton's equation of motion invariant. They leave the form of Hamilton's equation of motion invariant, which is important. Why they call canonical transformation? Because they leave the form of Hamilton's equation of motion invariant. We know Hamilton equation of motion is Qy dot is equal to del h by del pi and pi dot is equal to minus del h by del qi. Isn't it? Qi dot is equal to del h by del pi and pi dot is equal to minus del h by del qi. And this form remains same if the transformation is canonical. That is, if you transform from capital small q to capital Q and small p to capital P, then capital Q satisfies this also equation that capital Qi dot is equal to del by del of capital P of something, maybe K, maybe a constant which is stated as a Hamiltonian for that system, and capital Pi dot is equal to minus del K by del capital Qi. Okay, the form of Hamilton's equation remains invariant if the transformation is canonical transformation. Okay, if we consider a new set of variable capital Qi and capital Pi, so that they are function of small qi and pi, and according to the property of canonical transformation, there exists some function k such that capital Qi dot is equal to del k by del pi and capital Pi dot is equal to minus del k by del qi. Oh, sorry, and no vector symbol. Capital P dot is minus del k by del. The function k plays the role of Hamiltonian in new coordinate system. Okay, the form is invariant in canonical transformation. So let's, but from Hamilton's principle, we know that for exact path of motion, integration of Lagrangian del t from t1 to t2 is a constant or stationary. So that its variation is zero from Hamilton's principle. We know that for exact path of motion, integration of Lagrangian, L is Lagrangian, L dt has a stationary value. For a, from motion from 1 to 2 has a stationary or constant value. So if it is constant, so its variation will be zero. So delta of this will be zero. We know this. But Lagrangian is equal to, we also know that L is equal to summation of Pj Qj dot minus h. You know it from last class, we know that Hamiltonian and Lagrangian are equation by the equation h is equal to summed over Pj Qj dot minus L. From this you can say L is equal to summation of Pj Qj dot minus h. Summation, where is subscript, there is a summation. Actually in books it is not written, because there is a subscript means there must be summation. Summation of Pj Qj dot minus. Okay. So in new coordinate this Lagrangian will become summation of Pj capital Qj dot minus k, because here is k played the role of h in new coordinate system. So delta of that L0, delta of summed over Pj Qj dot minus k is equal to 0. Okay, these two right hand side is 0, so we can combine these two. Also besides this, we can also add a term, another term, variation of a function del f by del t dt is equal to 0, where f is a function of small qj, small pj, capital Qj, capital Pj and t. If that, then and from time t1 to t2 is so that this integration is a constant and the variation is a 0. Okay. There is a function you can write it in terms of its component. This is a function of small qj, small pj, capital pj t. We can write del f by del t is equal to del f by del qj and del qj by del t, del f by del plus del f by del pj and del pj by del t, del f by del capital qj, del f by t, del f by del capital pj, del f pj by del t, or del f by del t. Yes, sir. And here this f is known as generating function. So generating function is a function of small pj and capital Pj t. So that the transformation small pj to capital Pj is canonical. Okay. So now we combining these three. Here right hand 0, it is 0, 0. If you combine these three, left hand side gives you delta of pj qj dot minus
Sir,
k.
sir,
Huh, huh.
there is a like characteristic function and generating function. What are the difference?
Generating function means from that function we actually generate all kind of transformations are generated. Uh, Characteristics function is another one. We discussed that actually comes in Hamilton Jacobi theory. A particular term is called characteristic function. Okay, we discussed that later. Generating function here means from this f all kind transformations are generated. It contains all forms. It is fun- f is a function of all parameters, old parameters and new parameters and time. Okay.
Okay, sir.
Okay. Character function we discuss in the next slides or in the
Okay, sir.
next section actually. Okay. Hmm. So now we add these three. The right hand side is 0. So if we multiply something into 0, for simplicity it will be 0. Lambda and 0, 0. So and we add them. So if you add delta pj qj dot minus k, lambda and pj qj dot minus h, multiply lambda with small coordinates plus df by dt is equal to 0. Where f is a function of all coordinates. So for the validity of this above equation, what do you say? Since this is arbitrary, that this is equal to this integrand must be 0, which implies that lambda pj q lambda is multiplied here with small pj qj. Lambda small pj qj dot minus h is equal to capital pj qj dot minus k plus df by dt or del f by del t. Okay. Mm, Actually, is lambda is equal to 1, we call it a canonical transformation. Lambda is not 1, we call it extended canonical transformation. So for canonical transformation, this lambda is equal to 1. What we discuss what is given in our course. For extended thing, lambda is not equal to f. So what is your df? So here you see summed over pj qj dot minus h is equal to summed over capital pj qj dot minus k plus df by dt. Okay. So what is df? So we can write df since h is Hamilton and k is equal to t plus b total energy, which is a conservative system constant. So k, which is the Hamiltonian for new system, it is the total energy of the new system. It may be a constant. Mm. So when we take variation, we comparing this, we can write what df by dt. So now what is df? We have to integrate dt. If we integrate it dt, actually this qj dot means dqj by dt. Dqj by dt. So when we multiply dt, dt cancel, so dqj. So it's summed over pj dqj. Then h when multiplied dt, h is a constant, or there is no impact on dt integration. and k is also a constant. But this term d capital Qj by dt into dt answer is capital Qj. So from this we can say df is nothing but the uh, sum over j small pj dqj minus capital Pj dqj. We take to this side, that is minus. Which is a, that means df is this means it is a exact differentiable function. We can calculate df. The sum over pj dqj minus capital Pj dqj must be the exact differential means df. It is something derivative or you can say uh, differentiation of some quantity. Then it is called a canonical transformation. For a canonical transformation, this difference summed over j pj small pj dqj minus capital Pj dqj must be exact differential. We see in one two problems. Okay. So already we discussed in the last class a transformation is canonical if the Poisson bracket uh, gives 1. We know small qj pj is equal to 1. So Poisson bracket remains invariant. Capital qj pj is equal to 1. Then we call it a canonical transformation. It is another way to check. We can check also sum over j small pj dqj minus capital Pj dqj is a perfect differential. Okay. So equation 3 gives, this is the equation for canonical transformation, lambda is equal to 1. So we got sum over pj qj is equal to sum over small pj qj plus df by dt. Plus df by dt minus. Okay. Where f is called generative function of the transformation and f is a function of 4n plus 1 value. N small qj, n number of small pj, n number of capital qj, n number of capital pj and t. So it is a function of 4n plus 1 variable. Which are only 2n are independent coordinates because other two coordinates are connected to transformation equation. We have transformation equation capital Qj capital Pj is a function of small qj and small pj. So there are 2n transformation equations. Write that these two. There are q1 is something, p1 something. So there are and here n. So n number of transformation equations. Another n number. N means degree of freedom. What you can say. So there are 2n number of transformation equation. We have 4n plus 1 variables. And so we need other, if we leave the time, then other 2n variables are unknown. So we search for 2n other things or independent coordinates which can be given by 2n set of equations. If a is a function of both old and new coordinate, so from f contains or f is a function of that 2n plus 1 variable. 2n are known transformation equation. Other 2n plus 1 variable, if we remove t, then only 2n variables. So f is a function of those 2n variables. And in simplicity, we take 1n. One coordinate vary from n, 1 to n. Whether it is small q or small p or capital Q or capital P, it varies from 1 to n. So for simplicity, for when we say f is a function of 2n variables, first n are from old coordinate and second n from new coordinate. That means the first one is a function of a small q or small qj, then it may be second coordinate capital Qj. But it is optional. It is one kind of generative function, which is called f1. Another way possibilities, f may be a function of small qj, capital Pj, and t. Let's say f2. Another kind function is possibilities, f3. It is small pj, capital Qj, And another possibility is small pj, capital Pj. Okay, so there are only four possibilities, and we can name them four type of generating function: f1, f2, f3, f4. Clear? Hello? Or any
Yes, sir.
doubt? So we have only four kind of generating function. So f is a function of both old and new set of coordinates. Hmm, okay, if you take an old coordinate and n new coordinate, so you have four possibilities. Now generating function of first kind. At the day, from this equation actually we found f. It was already written. Sum dot pj small pj q, small q means small pj qj dot minus s is equal to sum dot capital pj qj dot minus k or df by dt. These are four kind of generating functions. Uh, so first kind is function of small qj, capital qj t. So if the function, then what is the df by dt? Easily we can write, since it is a function of small qj and capital qj, sum of j del f by del qj into dqj by dt, which is qj dot. So sum of j del f by del capital qj into qj dot means dqj capital qj by dt. Okay, plus del f by del. Uh, So now put this in equation here. In place of df by dt, you put this value. So what do you get? And the plus and compare the coefficient. Okay, putting this, I got this equation. Left hand side remains same, this two term remains same, and this one del L1 del qj qj dot del F capital qj qj dot plus del F1 del t. Now compare the coefficient of here. You see this equation is equal to, so left hand side coefficient must be matched with right hand side. Here qj dot, small qj dot is multiplied with small pj, but here in right hand side del f1 by del qj is multiplied with small qj dot. So by comparing, we say small pj is equal to del f1 by del qj, because here my f1 is function of small qj and capital pj. I already, so other two will be derived from f1. F1 is a function of small qj, capital qj. So other two variables are small pj and capital Pj calculated from these equations. So small pj will be calculated as del f1 by del qj. Next thing, here you see the small qj dot is multiplied with the pj, and here del f1 by del qj. For right hand side, left hand side, there is no qj dot. Means qj dot is multiplied with 0. This implies pj plus del f1 by del qj is equal to 0, which implies capital Pj is equal to minus del f1 by del capital Qj. Okay. Because Pj plus del f1 del Qj is equal to 0. Then third thing, other left thing are uh, s minus s minus k df1 del t. So you can write k is equal to, if I k to left hand side, h comes to the right hand side, h plus df1 by dt. Okay, hello?
Yes,
Yes, sir. Yes, sir.
So in this way, we actually calculate the unknown variables from known generating function. For f1 case, it is a function of small qj, capital Qj. So we calculate small pj and capital Pj from this formula. And k Hamilton new coordinate will h plus df1 by dt. This is true for all four type of generative function f1, f2, f3, f4. But these two vary because second one is our function of other very small q, capital, what we have written Our second one is a function of small q, capital B. So here unknown are small p and capital Q. Okay, this is another formula. Okay, these are the formula we got. Then go for case 2. Case 2 is then small qj plus capital Bj function. When we derive this, actually we take f is f2, second kind of generating function minus summed over capital Qj, capital Bj. So that here our previous case f1 is a function of small qj, both small qj and capital Qj. Here we in place of f we put same function small q and capital B, but here f2 contain capital B, but we need capital Q. So we if subtract small q capital Bj cancel this type of form of small qj. So it is a generating function of second and f2. So f in terms of f2 can be written like this. So then what is the df by dt? And df by dt will become del f2 by del qj del dqj by dt, del f by del pj dpj by dt, and so on. So if you put this left hand side is pj qj remains as, we got this equation like previous one, and compare the coefficient of here unknown are known are small qj capital pj. So we compare coefficient of small qj dot capital pj dot. Okay. Small pj dot comparing here, sorry, small qj dot first comparing, we got this pj is equal to del f2 by del qj. Comparing capital pj dot, here pj dot is multiplied this, and here pj dot is multiplied this. Both are in same side, okay, left hand side will be plus. So qj is equal to del f2 by del capital pj. Okay, and HK are same, HK are related in the similar fashion like one case or F1 case. Okay. Similarly, for F3 third function, we take f is equal to f3, which is a function of small pj capital qj. First one is small pj capital qj. So and when we take exact f, we actually need qj here. So it will be a sum of qj pj. Okay, and small pj. Whereas small q is always multiplied small p, and capital Q multiplied capital P. So it is small pj. So you take df derivative df by dt. We got this. Okay, in function of del f by del pj, and so h finally we got pj qj dot this. Compare here known variables are small p and capital Q. So we compare the coefficient of small pj dot and capital qj dot, because here this term will be actually cancelled from both sides. So small pj dot is actually multiplied with del f3 by del pj, and here qj. So both are in the same side. So I have to take one to left side, will be minus. So small qj will be minus del f3 by del pj. Okay. Similarly, if you compare the coefficient of a small qj dot, capital qj dot, we got capital Pj is equal to del f3 by del qj, del f3 by del qj, and k is equal to s plus del f3 by del t. Okay. Please 1 minute. Okay. So next we go for case 4 or the F4. So F4 is a function of small pj, capital Pj and t. So for that case, f is equal to f4 plus summed over small qj small pj minus capital Qj capital Pj. Both 2 and 3 we add here actually 2 and 3 case, in 2 case minus summed over capital Qj pj, and case 3 addition of small qj pj. If you add both these two, you got the fourth case f. F for fourth situation is f4 plus small qj minus capital Qj pj. And again comparing the coefficient of small pj dot and capital pj dot, small pj dot and capital pj dot, you can found that small, what are the relations? Small qj is equal to del f4 by del pj, and capital Qj and Qj not dot. It is small Qj is equal to minus del f4 by del Pj, and capital Qj is equal to del f4 by del Pj. These are the variables which can be derived from generating functions. So what kind of generating function is given, we can derive the unknown variables by using these formulas. Okay, you can simply remember these formulas are same. Both case, suppose here fourth case, we know already this in terms of small pj and capital Pj. If a function is given in terms of small pj and capital Pj, we can calculate small qj and capital Qj using this formula. Okay, always it is qj means it is del f by del pj. Only difference in sign. If it is small qj, then its sign is minus. Is capital Qj, sign is plus. And reverse for pj case. That means if it is small pj, then sign is plus. Del f4 or del f by del qj. We write whether it is 1, 2, 1 or 2, same formula. And if it is capital Qj, then it will be minus del f by del capital Qj. Okay, I have to remember these are the four generative functions. Any doubt?
Using these relationship, how can we find the generating function?
Generating functions from this relationship we also found by substituting in place of f. F is generally f is a function of either small q capital P, or small q capital Q, small p capital Q, small p capital P. Okay, so if we know this quantity P is the formula, okay, so from here we can calculate. We here del f is equal to pj into del qj. So what is f? F is integration of pj del qj. We get one integration means some value plus a constant. It's not complete one. Again from this formula we have know that, so f is equal to integration of capital pj into dqj minus integration of this f. It is another, we get another thing plus c. Then we compare. If this here c means is a constant in variable is qj, so constant p. This is a function of p. Here is a function of q. Okay. If you exactly match this thing, then you add these two and say for this case generative function is this. Okay, we see if there is a problem. I think I did one problem or not. Oh, here is a problem. Okay. Okay, this clear. Now come to this problem. What you ask? In the question, a canonical transformation relates the old set of coordinates small qp to new set of coordinate capital QP by the relations. Capital Q is equal to q square, small, and capital P is equal to small p by 2q. Find the corresponding time independent generative function. Here time is not a function of time. What you ask? This is example of that or not?
Yes, sir.
Yes,
You
sir.
want okay. we solve it. So given capital Q is equal to Q square, capital P is equal to small p by 2q. But according to our formula, okay, we know capital means it is a function of del F by del Q. Okay, what you let capital P means it is a function of, okay, sorry, capital Q or capital P. We have four relations basically. These four relations: small q minus del by small p, capital Q plus del by small capital P, capital P and del by del small q, sorry, small p del by del small q, capital P minus del by del capital Q. We have four formulas. Here we said small p is equal to del f2 by del q. Why you choose? Because these are unknown for f2. F2 is a function of small q, capital P, and most of the cases when no direct function is given, we follow this formula or f2. F2 is we use in general, we use f2 in all cases. If exactly not given, we use f2. So okay, because it is one q coordinate and one p coordinate. So according to the formula, for NEF this formula is same. Small p is equal to del f by del q, and capital Q is equal to del f by del p. For NEF, it is true. Okay. So we take f2 here. So we got small p is equal to del f2 by del q. So what is f2? Integration of p dq. So integrating, we found this q square p plus function of p. Okay, similarly for f2, integrate q square p, we get q square p function of q. If you match, same result we get. So f2 is equal to q square p. Hello? Hello? Again. Okay, so what is it? Okay. 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 Clear? So we can calculate by integrating these two. And here integration gives same result. Q square p, and here constant. We constant means here variable is dq. So constant is a function of p. Okay. Here integrating we get same q square p. Here variable dp is a function of q. We take it. But comparing these two, we get same result. Q square p plus a constant. Q square p plus constant. That means constant is 0. Or any constant you can take. So f is equal to q square p. This constant is same. Or simply to take 0. Clear?
Ye-
Hello? Or in doubt?
Yes, sir.
When it is given, we take integration. Like this. Then another problem: a mechanical system is described as the Hamiltonian. Uh, a simple harmonic oscillator p square by 2m plus half m omega square q square. If we take a canonical transformation generated by small f function of small q capital Q, that means that f1 is equal to capital Q by small q, then find the Hamiltonian in terms of new coordinate capital Q and capital P. So Hamiltonian is a function here given small p small q. We have to transform it in terms of capital Q capital P. Generative function is given. So we want to know other two variables. So small p by formula is equal to del f1 by del q. Here one component means there is no q1 q2 qn, only q1 q. Oh, okay. And similarly, capital P is according to formula is equal to minus, I think minus del f1 by del capital Q. What have I written? Minus. Capital P is minus, small q is minus. What do we have? Uh, okay, use these two formula. Then calculate small p. So what is the value of small p? Tell me what is the value of small p from this equation? Hello? Take derivative with respect to q. Hello, am I audible?
Minus q by q
Ah,
square, sir.
minus
Like
minus
plus q by q square.
capital Q, small q. Okay. Then what is capital P? What is capital P? Simply minus del F by del capital Q. Take its derivative with respect to minus capital Q.
So minus 1 by q.
Minus here also minus. Here minus plus. So it will
Plus
be
1 plus
plus
1 by
1 by small q. So we know that capital P is equal to 1 by q and the small p is equal to capital Q by q square. From here you can write, so what is the value of, so in place of small p you can put capital Q by q square, or here q is equal to how much? 1 by capital P. So we have to write Hamiltonian in terms of capital Q and P. So we know that small q is equal to 1 by capital P, q is there, and another small p is equal to, uh, put here q 1 by p. So q square will be 1 by capital P square or q by 1 by q p square. Put small p is equal to q p square and small q is equal to 1 by p. Then write the Hamilton. Then got the Hamiltonian. Okay. So in write this we get this type of Hamiltonian. Clear?
Yes, sir.
Uh, so uh, the Hamiltonian system generalized coordinate momentum of this. Another question: the Hamiltonian of a system of generalized coordinate and momentum is given h is equal to small p square q square. Find the solution of Hamilton's equation of motion. It's very simple. You know the Hamilton's equations. Q dot is equal to del h by del p and p dot is equal to minus del h by del q. From q dot del h by del p, if you take derivative with respect to p, we found it will be 2pq square. But q dot means dq by dt. Dq by dt is equal to pq square. Dq is equal to 2pq square dt. Dq by q is equal to 2pq dt. Okay. From this equation we found pf dot minus pf minus dot minus del s by del q, which is equal to, we take derivative, minus 2q p square. So dp is equal to minus 2q p square dt. So dp by p is equal to minus 2qp dt. Okay. Left hand side is this, right hand side is same. If we take only minus here, then right hand side is same. So I can write that del q by q is equal to minus del p by p. From this we got, actually taking its integration, ln q is equal to minus ln p plus ln a, q is equal to a by p, pq is equal to a. Okay. From this you can also get exact value of P and Q. So dP by dt is given. Then dP by dt is given by comparing. We have P is this and putting here PQA. Q is equal to A by P, A by P T20. Okay, this is another problem. This is another problem. Moving a positive constant, the moment of position respectively. Find the energy. Okay, you can do its energy. It's not necessary. Uh, come to, okay, we see this problem. The Hamiltonian of a classical particle moving in one dimension is this, where alpha is a positive constant. Here p and q are the momentum and position respectively. Find the available volume of the phase space of the system in terms of the energy. So harmonic oscillator type phase space. So this equation is given: p square by 2m plus alpha q square. Phase space means, P is momentum and position space. And the plotting are, when we done, we take Q as the x-axis and P as the y-axis. So what is the phase space diagram we have, if you know the exact relation between P and Q, then we can only draw it. Okay. Already H Hamiltonian is given, and for a conservative system, we know Hamiltonian total energy. So E is equal to this P square by 2m. So P dividing E with each term, we got this. Which actually we know for harmonic oscillator actually a space elliptical. This is the equation of ellipse. P by A square Q by V means X by A, Y by B. So it is the equation of ellipse. So in equation ellipse A, X by A is equal to X coordinate is Q. So A is equal to E by alpha root over, and Y coordinate is this 2m root over. So area of the ellipse is equal to pi AB. Pi A is equal to E by alpha root over 2m root over, which is equal to this. So area of phase space for a this system is found to be this. And another thing, this area is must equal to in the ellipse variation of P dq integrate over whole space. Okay, so if you write P dq and P is equal to, from this equation we got, from this equation P is equal to how much, 2me minus alpha q square root over, and put that we got 2me also the equation, we know that, and this integration is how much, a square by 2 sin inverse x by a. So if you integrate, this integration gives you this. Okay. The area. Next question is important. So that this transformation is canonical. It is very difficult to show using the Poisson bracket, but it is easy to show through using perfect differential. We know that if it is a canonical transformation, P dq minus capital P dq is a perfect differential or df. Here only one coordinate is given, q. So q1, q2 or sum is not needed. So one coordinate. So if you prove this, then it is a differentiation of some quantity, then it is a canonical transformation. Okay. We have given small p and capital P. From this, we can say from first equation cot q is equal to capital P by MWQ. So from this you can calculate sine square, because cot, if no cot, then cosec square will be how much? Cot q. It take derivative of both sides, and cot q derivative is cosec square q dq, and this quantity derivative is d, because p and q are both are variables, so it will be dp by MWQ minus p dq by dq by q square, p by MW dq by q square. When we take derivative with respect to p, it will be 1 by m omega q into dp, and with respect to q, p by m omega into dq by minus dq by q square. Okay, so but 1 by cosec square is equal to sine square. So take this side, we found dq is equal to minus sine square phi into dp by MWQ minus pwq. Now check p dq minus capital P dq is how much? Okay, small p dq capital P into capital dq, as we have this. So capital P is also, we have capital P is equal to m, this one capital P. So capital P capital dq becomes, we have to take one as constant. We take small p q as constant. We don't want to substitute here small value. So we have to then convert all capital value to small value. So then we putting the capital P and dq, we get this one p dq plus q dp by 2 minus, because sin square cancel. So if you multiply this, first term m omega cancel, so only q dp by 2 here, q square cancel, m omega cancel, only p by 2 dq. p dq minus p by 2 dq. P by 2 dq, q by 2 dp, it is derivative of p q by 2. So actually it is f. So we write in a perfect differential. So this transformation is canonical. Okay. So when this kind of function is given particular trigonometry function, it is very difficult to check using Poisson bracket. So we follow this perfect differential case, and we have to show that the difference between small p dq and minus capital P dq is a perfect differential. Clear or any problem? Hello?
No, sir.
Uh, Then another one important question, but here we can use Poisson bracket. Hmm. Because you sin q cos d, even the derivative one is a derivative other. So in that case we use Poisson bracket. For this transformation is canonical. Question is find the value of alpha beta if this transformation is canonical. So if the transformation is canonical, Poisson bracket is 1 according to Poisson bracket formula. Del q by del capital Q, del p by del capital P, minus del q by del p, and del p 1. Okay. Because here we take the transformation is from small q to capital Q, sorry, capital QP to small qp, because small qp are given here. The transformation is capital Q. Suppose y is equal to fx means we know that our old variable is x and new variable y is fx. Y is 5x or 6x. Our old variable will be x. If a, then new variable will written like this. So here q written like this, p written like this. That means our new variable is small q small p. So here transformation is from capital Q p to small q small p. Okay. So reverse. So so here Poisson bracket formula, when you calculate this is equal to 1 means with respect to capital Q capital P. So with respect to capital Q, capital P, variables are capital Q and capital P. Variables are capital Q and capital P. Then Poisson bracket formula will be del small q. Actually, small q is U, P is B. Del Q by del capital Q, del P by del capital P, minus del Q by del capital P, del Q by del capital Q is equal to 1. So if you take the derivative, it will be Q this. So derivative with respect to Q, capital Q will be sin Q only, cos Q. So P alpha cos Q. Again this derivative with capital P. So it will be beta 2p beta minus 1 into cos Q, cos Q, cos Q, cos square Q. Okay. And it will be beta 2p beta minus 1 into 2p derivative. Okay. Similarly for this derivative, alpha 2p to the power alpha minus 1 into 2 and sin q. I take derivative with the q, 2p beta p minus sin q. So sin square and minus minus plus. So if you take the common 2p to the power alpha beta minus 1, alpha minus 1 beta, that means it will be 2p to the power alpha plus beta minus 1. Okay. Again 2 here, 2 beta, and this term has 2 alpha. So 2 you can take common, or 2 beta. But 2 beta, 2 alpha, this sin square is 1. That means 2 beta, 2 beta is alpha beta 1, cos square q, 2 alpha beta, 2 alpha, 2p alpha minus 1 sin square q. If one condition we take, for this will be 1. What is the condition? Right hand side 1. So left hand side we must be 1. So for simplification, if alpha is equal to beta, then we can take it common and sin square plus cos square become 1. Because there is no trigonometric term in the right hand side. So left hand side trigonometric term must be removed. How it can remove? If you take alpha is equal to beta. If alpha is equal to beta, then this 2 beta is equal to 2 alpha. We taking this term common, we get cos square cube plus sin square cube 1. Okay. And taking common, we got here alpha is equal to beta. So it will 2 alpha 2 beta, it will be cancelled to this term. So 2p put alpha minus 1 to this. So how it can be solved? If you take alpha plus beta is equal to 1, then this will be 0. So it is a constant term. So from this we can found alpha is equal to beta and alpha plus beta is equal to 1. Then these are the functions we already discussed. Another important thing is so that Poisson bracket is canonical invariant. It is very important from exam point of view. So we have to show if x, y are two functions, then its Poisson bracket with respect to small qp is equal to capital QP. By definition, okay. So here actually transformation is from small qp to capital QP, and obeying this formula, the general formula. How to prove it? Go to the left hand side. Let's say xy, or you can say fg, anything. Let fg be the two function or xy be the two function. It's Poisson bracket with respect to small q, small p. Is it? This is the definition. Del f by del q, del g by del pk, del f by del pk, del j by del qk. Now take g is a function of capital Q, capital P. Then del g by del pk will be g is a function of qp, f is a function of xy. Then del f df, we know del f by del x dx, del f by del y dy. Similarly here del g by del qi dk, lqi, and del y del p, del g by del pi and del pi. Okay. Similarly del g by del qk follow the same formula. I substitute this pk here and this qk here, then we get this only differentiation. We check it, summed of over k, I take another I variable I, del f by del qk into these two terms. Similarly minus del f by del pk into these two terms, and multiply each term and simplify. You see del from all the term, it will be del g by del qi. If you take this term common, it will be del f by del qk into del qi by del pk, and here del g by del qi, if you take del f by del pk minus del qi by del qk. Similarly for here del g by del pi, we have del f by del qk and del pi by del pi, and del g by del pi, we have del f by del pk and del pi by del qk. Okay, these four terms, and if you see, it will nothing but if you take summed over k from here to this, and here also k, this is a Poisson bracket of f qi, here Poisson bracket of f pi. So f qi qp, f pi qp. Replacing f by qk, f is any function of qp. So let's say f is equal to qk. If f is equal to qk, then qk qi is equal to delta ik. Similarly, if here qk pi is equal to here 0, actually delta means ik, qq Poisson bracket 0, qp Poisson bracket 1. But if qk pi, it will be delta ki. But if same qq coordinate, it will be 0. If same, then Poisson bracket will be 0. So it will be 0 and this term is equal to 1. So we have 1 means delta ki. That means all k's will be replaced by I, or I should be replaced by k. So we found del f by this term 0, del f by del pi, and ki means or I will be replaced ki, okay, qk pi qp. Okay. qk pi is delta ki, putting delta ki, I becomes k, or some del f by del pi will be del f by del pk. Clear? Hello?
Yes, sir.
This is important for example. So the transformation is canonical. Okay. Only if you substitute, get this. Similarly, you can find other variable Similarly, Fg by Qp, replacing F by Pk. First is Qk, then Pk. We got similarly it will be minus del F by del Qk. Fpk is equal to del F by del Qk. Fpi is equal to del F by del Qi. Similarly, you get these things. You write lightly. And substituting this, you get your equation.
Sir, any specific textbook for this?
Textbook you can follow Gupta Kumar Sharma, Classical Mechanics by Gupta Kumar Sharma, or Goldstein, uh, Herbert Goldstein. Our Goldstein will be slightly difficult. You can follow Gupta Kumar Sharma or Rana Jo, Jesse Upadhyay. There are other two books
Oh,
very commonly used. Okay. So now put these things here, then you got this FGQP. Oh, we have already proved this. This is Poisson bracket is invariant on our canonical transformation. Okay, to check this, all are written here. Okay, here. Then go to next things, phase space. Periodic motion is phase space. First part is clear or in doubt? Hello, hello. In doubt or everything clear? We go to second part. Okay.
Yes.
Hello. Okay.
Yes, sir.
Phase space. We already discussed about phase space in the last class. It is a position momentum space. There are particular two kind of motions, or there are some periodic motion. When we particularly discuss about periodic motion in phase space, periodic motion means we see there are some motions where it is exactly follow its path. Okay. This is one kind of periodic motion, exactly it traces the path. Another motion is like sine wave, cos wave. It is also a periodic motion. It has a time period, and not it. So periodic motion is there are two kinds of motion. Hello, both are periodic or not? In both the cases, we have calculated time period or not?
Yes.
yes, sir.
Yes, sir.
There are two kind of motions. Okay. Uh, uh, this here we exactly retrace the paths, so it will be closed motion, and another is we call it libration, and second one is rotation, because here if you change angle by 2 pi plus theta, we get the same result. So there are two kinds of motion I given, rotation, and one is rotation, another is libration or vibration. Okay. Periodic systems are those which repeat their state of motion after a constant interval of time, known as period. In the phase space, all such periodic systems need not retrace their paths. All are not retrace their path means the closed path, which retrace their path in phase space are called liberating system, and the type of motion is known as libration. In the libration, both Q and P are periodic function of time with the same frequency, and periodic motion of this nature will be found when the initial position of the system point lies between two zeros of the kinetic energy. If the system started its motion between two zeros of kinetic energy, suppose simple harmonic or simple pendulum case, simple harmonic motion in this case, actually this type of motion exactly retraces path. So when you draw it in phase space, it will be a closed path. Okay. Since QP returns to their original stationary value in one period, the system point retraces its steps in every period and the orbit in phase space is closed. This motion is characteristic of common oscillatory system such as linear harmonic oscillators. In the other kind of periodic motion, Q itself is not periodic, but it shows that Q is increases by some value. Q, let's say Q0, the configuration of the system remain essentially unchanged. Generally, Q0 is 2 pi. When we sine wave, cos wave, cos theta is same as cos 2 pi cos theta. The most familiar example is that a rigid body constant rotate about a given axis with Q as the angle of rotation. Generally, that is a rotation case. So increasing by Q by 2 pi, it produces no essential change in the state of the system. The position coordinate in this system is period. This type of periodicity is an angle of rotation. Here, the position coordinate is the angle of rotation. And the second type, this type of motion will be referred to as simply as rotation in, in contrast to libration. Okay. So libration means it is in phase space it gives closed path. Rotation does not give any closed path, but after a regular interval it repeats its value. That means basically there are, if you change the 2 pi or if you change the variable from q to 2 pi plus q, then we get the exact result. So this type of motion is known as rotation and this type of motion is known as libration. Both are periodic motions. Okay, rotation and libration. After Q0 it will be same value. It is important to note that both type of periodicity may occur in some physical system. In the same physical system, we can also find both rotation and libration. For example, a simple pendulum. We have already discussed about the Lagrangian of simple pendulum. If you remember, then we know Lagrangian for a simple pendulum is half m L square theta dot square minus mgl 1 minus cos theta, and this Hamiltonian will be p theta square by 2 L square plus mgl minus mgl cos theta. Okay, the length of the pendulum is L is fixed. We know that, so it's a energy. Energy is actually Hamiltonian. This one. Since mgl is a constant, we can remove that and now we write p theta square minus mgl cos theta. So energy plus constant is mgl. Constant minus constant is another constant. So E will be this. If we plot theta, variables are theta and p theta. We have energy depends on theta and p theta. So from this you can calculate p theta will be this. We have three cases here. If you p theta, if E greater than mgl, E less than mgl, and E is equal to mgl. E is equal to E plus mgl cos theta. Oh, here plus, that is mgl 1 minus cos theta. Here only from plus mgl 1 tick. Okay. So p theta has this value. So we have three cases: E greater than, E less than, and equal to mgl. When E less than mgl, if E less than mgl, then, and you know cos theta varies between minus 1 to plus 1. So physical motion of the system can only occurs if for the theta value which cos theta is equal to minus E by mgl. Okay. Under this condition, the pendulum oscillates between 1 theta prime. It gives a periodic motion time. Okay, check here only. So if we actually plot the phase space diagram of this theta p theta, we got this type of curve for a simple pendulum. How we actually check it is descriptively given here. Three cases. for energy equal to mgl. When energy equal to mgl, E is equal to mgl, then we have a cos theta value minus 1, varies between -1 to +1. So this bracketed quantity have a larger value because E is equal to mgl. When mgl cos theta is equal to E, only that case it will be 0. Otherwise, it has a value. Uh, Most of the case, E is equal to mgl. So when cos theta minus 1, E minus mgl, it will be 0. P theta will be 0. And when it will plus 1, then it will be 2 mgl. Okay. So P theta 0, one case P theta 0. P theta 0 means these are the P theta 0 case. Mm. Similarly, all case we have a p theta 0 case. It is plotted here. Details given here, description. But we can easily also plot this using the equilibrium condition. Okay, which I am discussing in the next page. Then we
Sir, excuse me,
ah
sir. Sir, this question is correspond to which part of the our study material?
phase space. We have a written phase space, and okay, which unit is telling okay. We have a phase space. Unit. Unit 3, Hamiltonian phase space and applications. Hello?
Okay.
हाँ वहाँ पर लिखा हुआ है phase space for a system with 1 degree of freedom, phase flow. Actually, this comes under phase flow means phase diagram. Okay. Right, little. So, want to discuss some problems. If you plot the phase diagram of simple pendulum, it look like this. How it will check? Okay. Uh, okay, come to that point. This is actually it can be calculated from equilibrium case. We know there are two kind of equilibrium when we discuss about small oscillations: stable equilibrium and unstable equilibrium. At equilibrium point, force is zero. At equilibrium means force is zero, but for conservative system, force is negative gradient of potential minus del V by del X. Okay. Mm. So potential either maximum or minimum for a equilibrium case. So how you check whether V is maximum or minimum? You have to take its second derivative. If second derivative is less than 0, then V is maximum. If second derivative greater than 0, then we call it minimum. In phase diagram, actually, we discussed in the last classes that all at equilibrium position system is at rest. So for 0, a stable equilibrium only executes simple harmonic motion. Stable equilibrium means potential is minimum, that is del square V by del X square greater than 0. That is stable equilibrium point. In phase space, it is important because stable equilibrium point is either a origin or we can um, in phase space, stable equilibrium point act as origin and unstable equilibrium point act as a saddle point means intersecting point. If a point is a stable equilibrium, then it will be a origin, and if it is a unstable equilibrium point, then at that point actually phase trajectory is intersect. Intersect means the touch asymptotically they intersect, saddle point, crosses each other. So the two paths of constant energy in phase space interact at the saddle point. So if a system is given, we have to first calculate its potential energy. From the potential energy, you can predict its phase trajectory. Yeah. By if you have to check stable and unstable equilibrium point, then you can learn. Okay. Mm, all the other things are written. Okay. See, for example, what simple harmonic oscillator. For simple harmonic oscillator, potential is half kx square. So at equilibrium del V by del x is equal to 0. So which is the equilibrium point? If you have kx square, then its equilibrium point means derivative will be 2kx is equal to 0. So ax is equal to 0. Ax is equal to 0 is a equilibrium point for simple harmonic oscillator. Next our aim is to check whether it is a stable equilibrium or unstable equilibrium. Okay. So check del square V by del x square at x is equal to 0. Del square v by del x square is equal to how much? K. 2kx and derivative 2 again. So kx k
Yes, sir.
k. And independent x, so k. Generally force constant k is equal to how much? You know omega k by m root 2 over omega k by m root 2 over. So k is equal to m square omega. Sorry, m omega square. K is equal to m omega square. Mass is a positive quantity and frequency square means a positive quantity, frequency positive. So K is always positive. So K greater than 0. K greater than del V square by del x square greater than 0 means V is minimum. So it is a stable equilibrium point. So stable equilibrium point means it is a origin. So phase space is just like a making origin a path in the periodic motion, and it is a closed path. Closed path to the origin is at 0. So basically it is a ellipse. And why there are number of paths? Because changing energy. It depends on energy. If energy is changing, then one path is like this. Sorry, one path is like this. Another if changing energy, k value here say. Another path are. So this is the simple for a simple harmonic oscillator. See, if we apply this for simple pendulum, what you discuss here, you can also follow the same path. What is the potential energy for simple pendulum? MGL 1 minus cos theta. Okay. Where is it? This. MGL 1 minus cos theta. This is the potential energy. And find the equilibrium point. And equilibrium point, this derivative will be 0. What is the derivative? Here variable is only theta. So MGL minus MGL cos theta minus MGL cos theta. It is MGL sin theta. Minus sin theta derivative minus cos theta. A cos theta derivative minus sin theta minus plus. So MGL sin theta is equal to 0. So what is the value of theta? That means MGL divided sin theta is equal to 0. Then theta is equal to how much? Sin theta is equal to 0. Theta is equal to
Zero.
only 0.
0 and 2 pi.
Pi?
Pi also, sir. Yes, sir.
No. Right. N pi. If sin theta is equal to 0, theta is equal to n pi. You know it? Also 0,
Yes.
pi, minus pi, 2 pi, or plus minus n pi you can write. And 3 pi all are 0. So next your aim is to check that equilibrium point 0, pi, minus pi are stable or unstable equilibrium point. Then take its second derivative. MGL sin theta, then second derivative means MGL cos theta. So MGL cos theta is equal to 0. Sorry, MGL cos theta. Put value theta is equal to 0. If theta is equal to 0, it will be MGL positive. greater than positive means greater than 0. So obviously it is a potential energy minimum. So it is a stable equilibrium point and it is a origin. Theta equal 0 is a origin. When you put theta pi or minus pi, uh,
Will be MGL or minus N?
uh, minus cos pi is minus 1. Cos minus pi is also minus 1. So minus means potential is maximum. So they are saddle points. They are intersect points. See with the figure. 0 is the origin and pi minus pi are saddle point based on the intersect. Okay. These are the diagram. You can also plot knowing the stable and unstable equilibrium point. Okay. The details are not in your syllabus. Sometimes you may ask write the diagram with the for simple harmonic oscillator. You can plot like this. We already discussed for simple harmonic oscillator. If the equation is a ellipse, so obviously you will write ellipse. But from its potential, you can also plot this. Another example is for a perfectly elastic ball bouncing normally between two walls. Draw the phase trajectory. If it is moving between two walls, what is the phase trajectory? Okay. If moving the two walls means freely moving, so there is no potential energy or its total energy kinetic energy, like p square by 2m is equal to e or p is equal to plus minus 2 me. Okay, so either it's p is equal to plus 2 me or minus 2 me. Actually, when going into plus 2 me, returning minus 2 me. So this is just like a okay rectangle. There are also other examples. Okay, I'm not going to that. Uh, yeah. Next is one is your action angle variable. Okay, I think we'll discuss it in the next class. Okay, hello, I'll discuss it in the next class. Any doubt? Or tell me. Any doubt? Hello.
No, sir.
No, sir. We'll look into them.
Okay.
We'll get you.
Okay, we
We'll
have
solve.
only few things. Okay, and this action angle variable, least action principle, and Liouville's theorem, and other few two things, relativistic transform thing systems, Hamiltonian for relativistic systems, and harmonic oscillator. These three four things are remaining. We will discuss in the next two classes, which will be held on 5th and 6th. Okay. Other mostly we can cover 5 6 units. If you say which units are, suppose our first unit was symmetry, transformations, and Noether's theorem. We completely discussed that. And our second unit 2 is Hamilton's equation of motion. We already discussed that. Legendary transformation, Hamilton function, important property of conservation, and Rauthian. We all discussed that. Then unit 4, we have Hamilton's equation from variational principle. We only discussed the Hamilton equation from variation principle. We have to discuss in the next class Hamilton's principle from least action and action angle variable. And from unit 3,
Now, whatever we have discussed, that was unit 3, phase space
no,
for.
no, unit 1, 2, we have already discussed, and unit 3 only phase space. Unit 3 have Hamiltonian for a relativity particle. We discuss in the next class. Liouville's theorem we will discuss next class. We only
But
discuss phase space for a system. Only one part. Phase
okay,
space for a system with 1 degree of freedom, phase flow. All are 1 degree of freedom because one coordinate x. Whether it is simple harmonic oscillator or a simple pendulum, we only 1 degree of freedom we are discussing. And In the first part, what we discussed, it is in our unit 5, canonical transformation. Canonical transformation, generating functions. Okay. And we already discussed about unit 7 and 8, Poisson bracket, angular momentum, canonical invariance. All we discussed. Okay. Only we have two things to discuss. One is Liouville's theorem. Another is your harmonic oscillator as example, and particularly in gravitational field, and the gauge canonical transformation. The things. Okay. Next, we have two classes in fifth June and two classes in sixth June. We have to complete in that fifth and sixth. Okay.
Okay, sir. Thank you.
Okay, I am leaving. Thank you.
Hello, sir.
ଲୋକ ଘର ଦ୍ୱାର କରନା ସବୁ।
ଆଜିକାଲି ଶୁଣ ସାର୍ କିଛି ନଥାଉ ଘର ଖଣ୍ଡିଏ କରିଦଉଛି ଧାର ଉଧାର ହେଇଥାଉ ଯାହା ହେଇଥାଉ। ଘରକୁ ଦେଖିନା କହିବନି ଯେ ଏଥର ଅଳ୍ପ ଅଛି ବହୁତ ଅଛି।